Hello and welcome to this video on using the least common denominator, or LCD for short, to write equivalent rational expressions. Alright, so in this video I'm going to go over just a few examples where we're given a couple fractions, rational expressions, and first as to find the least common denominator of those fractions, and then second, rewriting those fractions as equivalent fractions where in which the denominator is that least common denominator, the LCD. Alright, so let's begin. So the first of these I've got for you. Here I'm asked to find the LCD, right, the least common denominator or least common multiple of the denominators of the rational expressions. Then rewrite each rational expression with the LCD, right? So again, I'm going to rewrite each of these fractions as an equivalent fraction where the new denominator is this LCD I'm finding. Alright, so we have 3 over 6a squared b, right, two variables a and b, and this other fraction where the numerator is negative 5 and the denominator is 20ab cubed, right? So all monomial polynomials, one-term polynomials in the numerators and denominators. Alright, so before I get on with that, let me do an example off to the side here where I work with just a couple numbers, and those numbers are, let's say I'm doing this for 1/6 and 9/14. Right? So 1/6, 9/14. So if you've been following my videos or reading your books and whatnot, and you could look for other videos if you wish. I have already gone over how we're going to find I've done a video on finding the least common denominator of two fractions, and a simple way to do that would be again to factor each denominator, just the denominators. Factor the denominators completely. So this denominator of 6 is 2 times 3 when you factor completely to primes. And the other denominator of 14, that breaks down to 2 times 7. Right? And then the LCD, right, the least common multiple of the denominators, or the least common denominator for short, is made up of a product of primes, right? Any prime that shows up in the factorizations of the denominators you see. So I have a 2, a 3, and a 7, right? So there's going to be 2 to some power, times 3 to some power, times 7 to some power, and the power that these are raised to is the largest number of times they appear in any factorization of the denominators. So 2, 2 appears once in this factorization, and once in this factorization there's a 2. So the largest of 1 and 1 is 1. So the LCD is going to have 1 factor of 2, 2 to the first, times, and then 3 appears once in this factorization of that denominator, and it appears 0 times in this factorization, but the largest again of 1 and 0 is 1. So you have 1 factor of 3 in the least common denominator. And 7, same thing. There are 0 factors of 7 here, 1 factor of 7 here. The largest of 0 and 1 is 1. So 2 to the first are just 2 times 3 times 7, right? So the least common multiple of the denominators, of the least common denominator, is 42, right? 2 times 3 is 6, 6 times 7 is 42. Well, okay, great. And then after that, right, so this is part 1. Right. And then after that, part 2 of this instruction is, now I'm going to rewrite these fractions as equivalent fractions with this 42, the LCD, as the denominator. So 1/6. Now if you would like, this is 1 over 2 times 3. If you want to write your denominators out in factored form, it might make it easier. You can leave it as 6, but I'll show you that I feel like writing it out factored might actually make things easier, because we're trying to change this denominator into the LCD of 42. Well, look at the factorization of the LCD. It's just 2 times 3 times 7. So what's missing? Right? What's missing is a 7. So I've got 2 times 3, and then I'm going to now remember, when you change a fraction to an equivalent fraction, something that has the same value, you're going to be multiplying the numerator and denominator by the same number. So that way it's like you're multiplying the whole thing by 1, right? Anything divided by itself is 1. And when you multiply by 1, right, values don't change. So all I need in the denominator to make it the LCD is the factor of 7. And again, you can't just multiply the denominator by 7. You must also multiply the numerator by 7. Right? And when all's said and done, I'm getting, multiply the numerators. 1 times 7 is 7, over, multiply the denominators, 2 times 3 times 7, that's my LCD here, right? 2 times 3 times 7, that's 42. Alright, so we're getting this statement here. Alright, 1/6 is equivalent to 7, 40/2. And this is a true statement. Right? A very quick way to check if two fractions are equivalent is to take their cross products. 1 times 42 is 42. 7 times 6 is 42. If the cross products are equal, then indeed these are two equivalent fractions. They have the same value. Great. And let's do the same thing with the other one. All right, 9/14. Again, if you want, I'm going to write that is 9 over, and then factor the denominator. 14 factors to 2 times 7. We saw it up here. And then all we're trying to do is rewrite it so that it has the same value but a new denominator, a denominator of 42, right, the LCD. So what's missing? Well, I have 2 times 7, factors of 2 and 7. The only factor that is missing that's in the LCD is 3. So I'm going to multiply the numerator and denominator of this fraction by 3. And again, it's both the numerator and denominator, so I'm multiplying by the number 1 technically, right? 3 divided by 3. And in doing so, 9 times 3, numerator, is 27. And then we have 2 times 7 times 3, which is the same as 2 times 3 times 7, right? It doesn't matter what order the factors come in. You'll get the same product of 42. Alright, and there's another, there is the equivalent of the original. So 9/14, right, is equivalent to 27 over 42. Alright, and again, if you wish to double check this, a quick check would be again to take the cross products. 9 times 42. Alright, so if you break it up, distribute, 9 times 40 would be 360 plus, and then 9 times 2 would be 18. 360 plus 18 is 378. And you can double check that indeed 27 times 14 is 378 as well. You can break up 14 to 10 times 4, or 10 plus 4, sorry, and do 27 times 10 is 270. And then 27 times 4, and then you break up 27 to 27. I know that's a lot. That'd be 80 and 28. That'd be 108. Then 270 plus 108, 378 again. You get 378 when you do the cross products either way. So indeed, these two fractions are equivalent. All right. So now, why are we doing this? The reason for this is going to be shown in a future video, or next video, probably the next one I make. The reason we want to get two fractions to have the have the same denominator is when we're adding and subtracting. So the reason I'm changing 1/6 to 7/42 and 9/14 to 27/42 is so then I can then add or subtract these numbers. Because if I said what's 1/6 plus, if I put a plus here, plus 9/14, we couldn't add them the way they look right now. We'd have to change them to these two fractions with the common denominator of 42. Same thing for subtraction, right? If I said what's 9/14 minus 1/6, we couldn't subtract them the way they look right now. They do not have the same denominator. We would have to change them to these equivalent fractions with a common denominator of 42. All right, so that is the whole purpose of this video, this objective, is so that we can add and subtract these fractions later. All right, so back to my first example with some variables here. I'm going to first find the LCD. All right, so part 1. I'm going to factor each denominator. Again, just focused on denominators, right? It's the least common denominator. So I'm going to take my 6a squared b and break that up completely. Now, I've mentioned in previous videos, we're going to treat factors with variables as primes. That doesn't mean they're representing primes. It just means we're going to treat them like a prime. So like a squared is simply a times a, b is b, and those don't break down anymore. But the 6 numerical factors we can break down further if we need to. So 6 we saw earlier, that's 2 times 3. And you can leave a squared as a squared if you want, or if you want, you can write it as a times a, same thing. Then times b, right? There's all the factors of this first denominator. And then 20ab cubed. 20 breaks down to 4 times 5, and the 4 would break down to 2 times 2, so you got 2 times 2, or 2 squared if you like. Nothing wrong with that. Times 5, that's 20. Times a times, b cubed, right? b times b times b. Or just write b cubed. So the least common denominator, right, or the least common multiple of these denominators is going to have powers of 2, right? There's going to be 2 to some power. 3 is a factor that shows up in these factorizations. 5, so times 5 to some power. There's some a's, right? A shows up and b shows up, okay? And now for the exponents on these, right? Let's see, for the factor of 2, remember the power on these, the exponent is the largest number of times it appears in any of the factorizations of the denominators. So 2 appears only once in this factorization and twice in this one, and the largest of those is 2, right? Twice. So you have 2 squared, 2 times 2, right? This is 4 as a factor of the least common denominator. Times, and then 3. 3 appears once and 0 times. The largest of those is 1, so times 3 of the first. 5 appears once in this factorization and 0 times up here. The largest is 1, so 5 to the first is in the LCD. And a appears twice in this factorization, right? A squared. You can also just look at the powers here if you want. 2 is bigger than 1. Appears twice here, once here. The largest is 2. So you have a squared in your LCD. And b appears, 3 times in this one, once in this one. Again, you can look back here at the powers. 3 is bigger than 1. So 3 is the power on b in the LCD. Alright, so the least common denominator is, 2 times 2 is 4, times 3 is 12, and then 12 times 5 would be 60. Right, so 60, and then you have a squared b cubed. Right, so there's the LCD. Right, part 1 is done. And then part 2 was I'm going to try to, rewrite these fractions. Let me throw a new paper here for some more space. I'm going to rewrite these fractions as equivalent fractions with this as the new denominator, this 60a squared b cubed. Alright, so part 2. So here we'll take the first one, 3 over 6a squared b. Now again, if you want, like I did with the numbers over here, you can write out the denominator factored if you wish, but I already have, I can look at this up here, right? So when I see 6a squared b, these are the factors, right? 2, 3, a, and b. So here comes the multiplication part, right? I'm going to try to rewrite this as a new fraction by multiplying by 1. Alright, now when I say multiply by 1, that means I multiply the numerator and denominator by the same non-zero number, or the same expression. So we're trying to make the denominator into the LCD. Alright, so look, here's the factorization of the LCD. Here's the factorization of my denominator now. What's missing? Well, this has 1, 2. I need another 2. This has 1, 3. Well, this has 1, 3, so I'm missing a 2, factor of 2. This has no 5s. The LCD has a 5, so times I'm missing a 5. And you can hopefully see that that's 10, right? 2 times 5 is 10, and 6 times 10 will give me the 60 that I need for the LCD. This has 2 A's. This has 2 A's, so I'm not missing any A's. This has 1 B. The LCD has 3 factors of B. So I'm missing B squared, or I'm missing 2 factors of B. You could write times B or times B squared like I have here. And I'm going to do the same thing to the numerator. Times 2 times 5 times B squared. Okay. And then when all said and done, this is equal to multiply the numerators. 3 times 2 times 5. Well, 3 times 2 times 5 is 30, right? 3 times 10. And then you have times b squared. So the numerator is 30b squared, and the denominator is the LCD, right? We have all the factors that the LCD does. So that's the 60a squared b cubed. Alright, so off to the side, right below it, I'll put our equivalents, right? So 3 divided by 6a squared b is equivalent to 30b squared divided by 60a squared b cubed. And then a little semicolon or a comma, and off to the side I'm going to put some little caveats here, little restrictions. Because yes, these fractions are equal no matter what you plug in for a and b, with a few exceptions. Alright, with a couple exceptions. So go ahead and let's see. Now remember, in previous videos I've made, or again, read your books and see what it means to be undefined. Right? This fraction will indeed be equal to this fraction for any value of a and b I plug in, just so long as the value I plug in for a and b doesn't make me divide by 0, right? I do not want 0 in a denominator anywhere. So look at the first fraction here, you have factors of a and a, right? This is technically a times a, and then a factor of b. So a can't be 0, right? Because if a were 0, this denominator, and this one too, right, would be 0. Because you'd have 6 times 0 times whatever b was, and anything times 0 is 0. So a cannot be 0, and at the same time, b, right, the value I plug in for b can't be 0 either. And you can see that over here, and you got b times b times b in the denominator, you got b in the denominator, you got factors of b in the denominator. And so that can't be 0 either. Right? Because if it were, you'd be multiplying by 0 here and then have 0 in the denominator, and again you can't divide by 0, and same thing over here, you'd have 0 in the denominator. And that looks like about it. Those look like the only restrictions. So there, that's it for that fraction. Okay, so this fraction is equal to this fraction as long as the values I choose for a and b are not 0. And you can go ahead and test it out. I think a very simple one would be just let a be 1 and b also be 1, right? Because if a were 1 and b were 1, you'd have 3 divided by 6 times 1 times 1, right? So 3 divided by 6 being equal to 30 times 1 over 60 times 1 times 1, so 30 over 60. And 3 divided by 6 and 30 divided by 60 are both 1/2, right? They'd both be 1/2. So they're equal in that case, and you can try it out with any other values you wish, right? Just so long as a and b are not 0, right? Not both 0. Well, as long as neither one of them is 0, actually. Right. So try that on your own. All right. Now the other fraction. Okay, the other fraction, and I'm going to pull in a new sheet here, just so I'll cover this one up. Hopefully you've seen this enough now. And then the other fraction is -5 over 20ab cubed. And again, you can write it factored if you wish. I'm going to say 20ab cubed. I have that factored here. Right, here's the factorization of 20ab cubed, and we're trying to make it look like this. We're trying to give it the same factors as this 60a squared b cubed, this LCD. All right, so I'm going to multiply by 1. Right, I want to change it to an equivalent fraction, so I'm going to multiply by 1, meaning the numerator and denominator by the same expression. All right, so 20ab cubed has 2 2's. So does the LCD, right? LCD has 2 2's, 2 squared. It has no 3's, but the LCD has a 3, right? So I need a factor of 3, and again the numerator as well. Multiply by a factor of 3. The 20ab cubed doesn't have, so it has a 5. So does the LCD, so that's not missing. It has 1a, but the LCD has 2 a's, right? A squared. So I'm missing one factor of a, so times an a in the numerator as well. And it has 3 b's. The LCD also has 3 factors of b. So the only things they're missing are 3 and a. Alright, so after the multiplication, the numerator, -5 times 3 times a, would be -15a over. And then the denominator, again, we're trying to make it look like the LCD, and it would be, right? 20 times 3 is 60. Then the a times a would be the a squared, and then the b cubed, right, times b cubed. There's your LCD. So indeed we have, this equivalence, right? So -5 over 20ab cubed is equal to -15a over 60a squared b cubed. All right. Again, off to the side, I'm going to put that, whenever there are variables in denominators, I'm going to put these restrictions. I want to make sure that I never divide by 0, right? Never have 0 in a denominator. And I have the same issue here as I did earlier, right, with the other fraction. I have a factors of a in these denominators, so a cannot be replaced by the number 0. And also, right, I've got factors of b's, actually 3 factors, but there's still factors of b in these denominators, so b cannot be 0 either. All right, so as long as those two numbers aren't 0, this is a good statement. All right, this fraction will indeed be equal, have the same value as this fraction, as long as I don't replace a and b with 0. All right, but replace them with anything else and you're fine, right? Again, an easy one here would be if I replace a and b with the number 1. If both of these were number 1, 1, 1, 1, you'd have -5 over 20, which is -1/4, -0.25 in decimal, would be equal to negative 15 over 60, which is again negative 1/4. So they would be equal. But try out other values. Plug in 2 for A and 5 for B and negative 8 for A and 20 for B. Plug in whatever you want for A and for B, as long as it's not 0, and you will see that this fraction is indeed equal to this fraction. Great. And one more time again, the reason we're doing this, right, the reason I change this fraction to this and this fraction to this is so now I'll be able to add them or subtract them. Right, these two fractions now have the same denominator, right, that LCD, the 60a squared b cubed. And so I'll be able to now combine them with addition and subtraction. Alright, but that's again for a future video. Alright, so I've got one more example here where I'm given two fractions and asked to find the LCD and then rewrite equivalent fractions with that LCD. Alright, so that example is here. So now these fractions, it's unlike the last example. The last example had a couple variables, but every single polynomial, right, every numerator and denominator had one term, was a monomial. Here my denominators are trinomials, right? They have 3 terms and they're quadratics and stuff, right? So maybe people would consider this a little more complex. I don't know. All right. So first, part 1, let's find the LCD, the least common denominator, least common multiple of the denominators of these two fractions. Alright, so the first denominator, x squared minus 4x minus 5. I'm going to, factor this completely. Alright, if you want to look at, I have a video up of factoring quadratics of the form ax squared plus bx plus c, if you want to look at that. Or read your book on, some section on factoring quadratics. Fine, I'm just going to go ahead to what it's going to factor to. This will be the product of x minus 5 and x plus 1. Right, so you got two factors. A factor of x minus 5, which again, we're going to consider this like a prime. It doesn't mean it's prime. It doesn't mean when I plug in something for x it's going to be prime. It just I'll just treat it like it's a prime. And then this other factor of x plus 1. Again, this whole thing, because it's got a variable in it, I'm going to treat it like it were prime, even though it wouldn't be if I replaced, x with 5 or something, right? If x was 5, this would be 6. That's not prime, but I'm going to treat it like a prime. Okay. Then the other denominator, x squared minus 7x plus 10. Alright, same deal, factoring a quadratic trinomial. This would factor to x minus 5 times x minus 2. Alright, so two factors. The factor x minus 5, which again I'll treat like a prime, and the factor x minus 2, and we're done factoring. Okay, so I factored them completely. So the LCD is going to have a factor of x minus 5 to some power, a factor of x minus 2, so times x minus 2 to some power, and also there's a factor of x plus 1 that shows up in these factorizations of the denominators, so times a factor of x plus 1, to some power. And hopefully you can see that the power on each of these factors would be 1, right? X minus 5 shows up once and once, right? So in each of those factorizations, x minus 2 shows up once here, 0 times there, the largest is 1. And x plus 1 shows up once up here, and 0 times down here, the largest is 1. Alright, and you don't really need to write the power of 1, right? Raising something to the first power doesn't change any values. Okay, so there's the LCD. This is the denominator I'm going to try to get for each of these fractions. Alright, so then part 2 is writing these as an equivalent fraction with this denominator, right, with the LCD. Alright, so here, this one, I am going to write my denominators in factored form, right? So, and to be honest, I'll say I personally prefer writing denominators in factored form to begin with, because later when we add and subtract, after the addition or subtraction, you get that common denominator and the denominators in factored form. After the addition or subtraction, if the denominator is already in factored form, it'll make it that much easier to simplify, meaning, divide out any common factors that the numerator or denominator might have. Alright, so this is, so personally I actually do enjoy writing my fractions in the beginning with their factored forms. So 5 over x squared minus 4x minus 5, that's 5 over x minus 5 times x plus 1. Right, this here is the same as x squared minus 4x minus, we saw it here. Right? Alright, so what I'm going to do is, again, I'm going to write an equivalent fraction. Right? So we're going to multiply this fraction by 1. So the same expression in the numerator and denominator. And just look at this denominator and look at the LCD that we're trying to change it into, right? This least common multiple of the denominators. It's got x minus 5, the LCD has x minus 5. It's got x plus 1, the LCD has x plus 1. So the only thing the LCD has that this denominator does not is the factor of x minus 2. Alright, so I'm going to multiply, and again, because it's got multiple terms, I'm going to put in parentheses. Same thing for the numerator. Right, multiply the numerator and denominator by this x minus 2. Right, so this is equal to 5 times x minus 2, again the whole thing. So if you'd like, you can distribute, divided by, and then the LCD, x minus 5 times x plus 1 times x minus 2. That's the LCD. I mean, I know the factors are in a different order, but it doesn't matter, right? A times B times C is the same thing as B times C times A. And when you're multiplying factors, it doesn't matter what order they come in. Okay, great. So my equivalence statement here. So my original fraction, right, the original fraction was this. That fraction is equal to 5 times x minus 2 divided by x minus 5 times x plus 1 times x minus 2. And again, if you want to, you can multiply all this out if you want. 5 times x is 5x, 5 times negative 2 is negative 10. So you could write the numerator as 5x minus 10. That's fine. You can multiply the denominator out too. I mean, this is all well and good though. All right, I'm going to leave it like this for now. Now, off to the side, right? Remember, yes, this fraction will be equal to this fraction, but not all the time. Not when the denominators are 0, right? You can't divide by 0. So again, looking at this process here, when I change the fraction to an equivalent fraction, look at your denominators. There's a factor of x minus 5. So x cannot be replaced by the number 5, right? That'll make that factor 0, which would in turn make the denominator 0. There is a factor of x plus 1. So not only can x not be 5, it can't be negative 1 either, right? Because that'll make that factor 0. And then there's also this factor of x minus 2 showing up. So x cannot be 2 either. All right, so here's my equivalence statement. Right here in the orange box. Right. So this fraction we started with is equivalent to this fraction with the LCD as the denominator only when the value of x is something other than 5, negative 1, or 2. And again, check it out, try it out, test it out. Replace x with some number other than these. So how about 0? All right, here I'll make a quick out loud test here. If x were 0, this fraction, the original one, the numerator would be 5, and the denominator would be negative 5. Right? So the whole thing would be negative 1. 5 divided by negative 5. This fraction would have a value of negative 1. All right, then over here, if x were 0, you'd have 5 times, 0 minus 2. 5 times negative 2 in the numerator, negative 10, divided by, and then negative 5 times 1, so negative 5 times negative 2 would be positive 10. You'd have negative 10 in the numerator, positive 10 in the denominator, so a value of negative 1, right? Negative 10 divided by 10 would be negative 1. So you'd have negative 1 for this fraction, negative 1 for this fraction. They are indeed equal when x is 0. Try it out with other numbers. Plug in 3, 500, a million, 1/5, 2/3. Plug in whatever you want, as long as it's not 5, negative 1, or 2, and this fraction's value will be equal to this fraction's value. Okay, great. And then the one last one, right? That was changing this fraction into a fraction with an equivalent fraction with the LCD. So take the other one. All right, again, hopefully you can see all this. Right, I'm going to cover it up. Got the next fraction coming up. Take the other fraction. Negative 3 over, and again, I like personally to write my denominators factored. So over x squared minus 7x plus 10, we saw that factored here. And that's x minus 5, the quantity x minus 5, times the factor, the quantity x minus 2. Alright, I'm going to multiply this by 1. I'm going to change it to an equivalent fraction. So I'm going to multiply the numerator and denominator by the same thing. And what's in the LCD that's missing here? Well, the only factor in the LCD that's missing here is the x plus 1. So I'll multiply by the factor, this quantity x plus 1 in both the denominator and the numerator. All right, and we get our equivalent fraction. The numerator is simply, again, multiply the numerator is negative 3 times the factor, the quantity x plus 1. And if you would like, you can distribute this. This would be negative 3x minus 3, totally fine, over, but I'm going to leave it like that for now. And then, multiplying these factors, we get our LCD, x minus 5 times the factor x minus 2 times the factor that was added or multiplied by x plus 1. Great. And so here's my equivalence statement. So my original fraction, negative 3 over x squared minus 7x plus 10, will indeed be equal to this fraction here, negative 3 times x plus 1, or negative 3x minus 3, whatever you want, divided by, and then x minus 5 times x minus 2 times x plus 1, right, that LCD. Now, again, this isn't always going to be true. Right? This is true as long as you're not dividing by 0. And you may have noticed I've got the same 3 factors showing up in this process as I did in this process, right? The factors of x minus 5, x minus 2 are showing up, and x plus 1. So the values I can't replace x with are 5, 2, and negative 1, right? So as long as x is not one of these 3 numbers, you're golden. These 2 fractions will indeed have the same value. And go ahead and check that out. Try it out with some numbers. Plug in 0 for x, 1 for x, 3, 6, a million, 10, whatever you want. As long as it's not these 3. And this fraction will indeed be equal to this fraction. Alright, and one last time I will say why are we doing this? Alright, why am I changing this fraction to this and this fraction to this? Well, again, it's for the purposes of being able to add and subtract the fractions. Alright, if I were to ask you, take this fraction and add this fraction, take this plus this, you couldn't do it the way they look right now. You need the same denominator. You need a common denominator to be able to add or subtract. So I would go through the procedure of changing these fractions to these fractions here, these 2, with the same denominator. Right? You see how they have the same factors in the denominator. They are equal denominators. And then I could combine them. Then I could add them or subtract them if I wished. All right. Okay, and that'll probably be the next video, right? Starting adding and subtracting fractions, rational expressions. Alright, so as I like to say at the end of these, please, try your best to understand, get and understand the material on your own first, because I find things stick better with people when they work through them on their own. You feel more accomplished and you tend to remember it better. Read through the material you're given. Read through it, author's examples. Try your best to understand them. Work them out yourself even. Practice problems in the backs of sections or whatever you're given. Worksheets. Check your answers if they're provided in the backs of books or on some paper or wherever. And don't just give up after the first attempt, please. Right? Don't get frustrated so quickly. If after several attempts of a problem you're still not getting it, try reading through the material again, reading through the author's examples again. Perhaps the second or even third read through, something will click that didn't click or make sense the first time through. You'll have like an aha moment maybe. But if after several read-throughs of the material and several attempts at some exercises, you're still not getting it, it's still not clicking, then it is not a sign of weakness whatsoever to go looking for help. That is what other people are out there for. Ask a teacher, ask a tutor, a friend in the class, or just a friend you know who happens to know the material. Look for videos online like this one on the subject, or plenty of other ones out there that are better than mine, I assure you. But look for videos online, look for supplemental resources, and just keep at it. Stay persistent, keep practicing, keep at it, and I know you'll get it eventually. I just know you will. And also try to have some fun with it. Keep a mental state that I'm enjoying this. If you're constantly saying I hate this, I hate this, I hate this, well, you're gonna hate it, right? Try saying you enjoy it to yourself a little bit. Make that a mantra for a while, and try to have some fun with it, and maybe it'll make it a little easier in the long run. And thanks for watching.